The biggest obstacle to reaching Proxima Centauri has nothing to do with distance. The universe has something far worse waiting. What if the nearest exit from our solar system is also the most hostile place we could possibly try to reach? So ask yourself, how well do you actually know your closest neighbor? If you're the kind of person who genuinely gets fired up about the cosmos, make sure to subscribe to the channel. Now let's get started. Proxima Centauri belongs to a class of stars called red dwarfs, and red dwarfs are the most common type of star in the entire Milky Way galaxy. They're smaller than our Sun, cooler, dimmer, and they burn through their fuel so slowly that many of them will still be shining long after our Sun has died. Some red dwarfs could theoretically remain active for trillions of years, orders of magnitude longer than the current age of the universe itself. On the surface, that sounds almost comforting. A star that lasts forever, a star that any planet in its orbit could theoretically count on for an almost incomprehensible stretch of time. But there's a catch buried in the physics of how these stars work, and it changes everything. Our Sun generates its energy through nuclear fusion deep in its core. That energy then has to make its way outward to the surface, and it does so largely through what's called radiation, a slow stuttering process where photons get absorbed and re-emitted, bouncing their way outward over thousands of years before they finally escape. This process creates a relatively stable, relatively calm outer layer. Our Sun has flares and solar storms, absolutely, but there's a kind of buffer, a cushion between the wild nuclear core and the surface we see. Red dwarfs don't have that buffer in the same way. Stars like Proxima Centauri are fully convective throughout, meaning the hot plasma from their cores churns all the way up to the surface in constant, churning currents. It's like comparing a carefully insulated pot of water to a pot that's boiling so hard it's splashing everywhere. All that constant churning twists and tangles the star's magnetic field lines in complex, unstable ways. And when those magnetic field lines snap and reconnect, which they do regularly, they release enormous bursts of energy in what we call stellar flares. Now our Sun flares too. Solar flares are a real thing, and when powerful ones hit Earth, they can disrupt satellites, cause radio blackouts, and trigger spectacular auroras. The famous Carrington event of 1859 was a solar flare so powerful it set telegraph machines on fire and filled the skies with auroras visible all the way down to the tropics. And that was considered extreme for our Sun. Proxima Centauri makes the Carrington event look modest. This star flares constantly, intensely, unpredictably, and in 2025, a team of researchers used the ALMA Observatory, the Atacama Large Millimeter-Submillimeter Array, which is one of the most powerful radio telescope networks ever assembled, sitting high in the Chilean desert at an altitude of around 5,000 meters, to conduct the most detailed study of Proxima Centauri's flaring activity ever carried out at millimeter wavelengths. What they found was genuinely unsettling. The team, led by Meredith McGregor at Johns Hopkins University, working alongside researcher Kiana Burton, captured 50 hours of continuous observations of the star. Over that period, they recorded 463 separate flare events, not over a year, not over a decade. 463 flares in 50 hours of watching. These weren't tiny, insignificant sparks. The flares ranged in energy from 10 to the 24th power up to 10 to the 27th power ergs. For context, a powerful solar flare from our Sun might release around 10 to the 32nd power ergs. So individually, these flares are smaller, but they are happening at a rate that is extraordinary, and the pattern of how frequently they occur, what scientists call the flare frequency distribution, was different at millimeter wavelengths than anything previously measured from optical telescope data alone. In other words, scientists who had been studying Proxima Centauri primarily in visible light had been missing critical information. McGregor put it directly in the published findings, and I'm paraphrasing here, that ALMA is the only millimeter interferometer sensitive enough to detect this level of activity, and that without those observations, the radiation environment around Proxima Centauri B was being underestimated. The danger was worse than the existing models suggested. Now think about what that means for Proxima Centauri B, the planet that has been sitting at the center of all our interstellar dreams. Proxima B is a confirmed planet, discovered in 2016 using the radial velocity method, detecting the tiny wobble the planet's gravity causes in the star's motion. It has a mass somewhere around 1 to 1.5 times that of Earth, and it orbits squarely within what's called the habitable zone of its star. The habitable zone is the range of distances from a star where temperatures could, in principle, allow liquid water to exist on a rocky surface. Earth sits beautifully inside our Sun's habitable zone. Proxima B sits inside Proxima Centauri's. That's the headline that captured the world's imagination. An Earth-sized world in the right zone, around the nearest star. For a moment, it felt like the universe had handed us a gift, but here's where the physics gets cruel. Because Proxima Centauri is so much cooler and dimmer than our Sun, its habitable zone is dramatically closer in. For a planet to be warm enough for liquid water around a red dwarf, it needs to orbit much nearer to the star than Earth orbits our Sun. Earth orbits the Sun at an average distance of about 150 million kilometers, what astronomers call 1 astronomical unit. Proxima B orbits its star at a distance of only about 7 million kilometers, roughly 1/20th of our distance from the Sun. At that distance, Proxima B isn't just in the habitable zone. It's essentially living inside the star's atmosphere compared to how we think about planetary distances. And that means every single flare, every one of those 463 events recorded in 50 hours, isn't something the planet experiences from a comfortable distance. It's something the planet takes almost directly on its surface. And these aren't gentle nudges of radiation. The ultraviolet and X-ray output during Proxima Centauri's flares has been measured to briefly increase the star's luminosity by factors that would be catastrophic for any unprotected atmosphere. The energy bombardment strips away ozone. It photodissociates water vapor, meaning it literally tears apart water molecules in the upper atmosphere, allowing the hydrogen to escape to space. Over billions of years, this process could strip a planet of its oceans and leave its surface bare and exposed to hard radiation. Proxima B have a magnetic field that could protect it? Possibly. In fact, a study published in May of 2026 found evidence suggesting Proxima B may possess a magnetic field, which, if confirmed, would be an important protective factor. Earth's magnetic field plays a massive role in shielding our atmosphere from the solar wind and keeping our air intact. If Proxima B has something similar, perhaps it has held onto more of its atmosphere than the bare models suggest. But here's the problem that even a magnetic field can't fully solve. At Proxima B's orbital distance, scientists believe the planet is almost certainly tidally locked to its star. Tidal locking is what happens when a world orbits so close that the gravitational pull of the star gradually slows the planet's rotation until it stops spinning relative to its orbit. The result is one face of the planet in permanent eternal daylight and the opposite face in permanent eternal night. No day and night cycle, no sunrises or sunsets. Just a scorching hemisphere baked by a flaring star forever, and a frozen hemisphere plunged into darkness forever. Our own moon is tidally locked to Earth. That's why we always see the same side of it. The same process at a much stronger magnitude likely happened to Proxima B long ago. And tidal locking creates another problem for magnetic fields, because magnetic fields on rocky planets are thought to be generated by a churning molten core, driven in part by rotational forces. A tidally locked planet rotates so slowly that its core may have little to no internal stirring, which means the magnetic field it can generate might be significantly weaker than Earth's. Some models suggest this, though the science here is still genuinely debated, and researchers are actively working to understand it better. So we have a planet that is bombarded by radiation at a rate astronomers are now saying is worse than previously calculated, a planet that is almost certainly tidally locked, a planet whose ability to maintain a protective magnetic field is in question, a planet whose atmosphere may have been eroding for billions of years. And yet, to be completely honest with you, in the spirit of the kind of science this channel believes in, we don't actually know for certain that Proxima B is hostile to life. We haven't been there. We don't have a spectrum of its atmosphere. We don't know if it has water or ozone or any of the chemical fingerprints we associate with life. All we have are models built from what we know about the star, the orbital mechanics, and our best understanding of planetary physics. The honest scientific position is, it might be habitable, it might not be. We genuinely do not know. But what we do know is that every new piece of data we collect seems to make the case for habitability harder to make, not easier. The ALMA results added another layer of concern, and that's before we even get into the next obstacle, something that has nothing to do with the destination itself, and everything to do with the journey, because even if you somehow solved the propulsion problem, even if you built a spacecraft that could make the trip in a human lifetime, even if you pointed it at the right coordinates and lit the engines, there is something between here and Proxima Centauri that almost nobody talks about in the headlines, something invisible, spread across the entire 4.24 light-years of empty space between our solar system and that star. If you are enjoying this journey, make sure to subscribe to the channel. You will be part of a community that explores the cosmos together. Something that, at high speed, could tear a spacecraft apart atom by atom. And now we're going to talk about exactly that. The interstellar medium, the space between the stars that isn't actually empty at all, and why traveling through it at the speeds we'd need to get there in any reasonable time is one of the most dangerous gauntlets in the known universe. If you think the distance was the problem, just wait. Here's something that almost never comes up when people talk about interstellar travel. Something that gets quietly skipped over in the headlines, the documentaries, the breathless announcements about new propulsion ideas. Something that sits between us and Proxima Centauri like a gauntlet nobody told you about. Space is not empty. I know that sounds strange. We've all grown up with the image of space as this vast, silent void, pure blackness, nothingness, a vacuum so perfect that sound can't travel through it. And compared to anything here on Earth, that's basically true. Space is incredibly thin, incredibly sparse, but incredibly thin and completely empty are two very different things. And when you're moving fast enough, really fast, the kind of fast you'd need to cross 4 light years in a human lifetime, the difference between those two descriptions becomes the difference between a successful mission and a catastrophic failure. The stuff that fills the space between stars is called the interstellar medium, and it is, in essence, a very dilute soup of gas and dust, mostly hydrogen, with some helium mixed in and tiny traces of heavier elements. On average, in the region of space around our solar system, there's roughly 1 hydrogen atom per cubic centimeter of space. That's almost nothing. You could take a cubic centimeter of the air in the room where you're sitting right now, and it would contain around 27 quintillion molecules. Compared to that, 1 atom per cubic centimeter sounds harmless to the point of being laughable, but here's where physics turns on you. The danger from the interstellar medium isn't about how dense it is, it's about how fast you're moving through it. Because when you push a spacecraft to a significant fraction of the speed of light, something profound happens to your perspective of every single particle in your path. From the spacecraft's point of view, it isn't a vehicle moving through a gas, it's a stationary object being hit, continuously, relentlessly, by a torrent of incoming particles, and the faster you go, the more energetic those particles appear to be. This isn't a metaphor, it's special relativity. The same physics that Einstein described over a century ago tells us that motion fundamentally changes the energy of particles depending on your reference frame. At 20% of the speed of light, the velocity breakthrough starshot was targeting, each hydrogen atom you encounter doesn't feel like a drifting, passive speck of matter. It hits the front of your spacecraft with the energy of a particle accelerator beam. You have effectively turned the gentle drift of interstellar gas into a constant, high-energy radiation bombardment aimed directly at the nose of your ship. Researchers who have studied this problem in peer-reviewed publications, including work published in the journal Acta Astronautica, have described the situation clearly. Interstellar gas, from the perspective of radiation safety, means that interstellar space is not an empty void. The oncoming relativistic flow of interstellar gas produces intense radiation that bombards the spacecraft, its electronics, and any crew aboard. At moderate relativistic speeds, around 30% of the speed of light, the radiation dose builds up fast enough that unshielded electronics would degrade to inoperable within minutes, not years, not decades, minutes, and that's just the gas, the hydrogen, the single atoms drifting quietly through the dark. Now let's talk about the dust, scattered through the interstellar medium. Mixed in with all that hydrogen are microscopic grains of solid material, tiny particles of silicate, carbon compounds, and ice. They're enormously sparse by any everyday standard. In the region of space around our solar system, you might find somewhere between a few hundred and a few thousand dust grains in every cubic kilometer of space. Agon sounds harmless, sounds like nothing. Until you do the math, a relatively large interstellar dust grain might have a mass of around 1/100th of a milligram. Tiny, barely anything. At normal everyday speeds, you'd never worry about it. But at 50% of the speed of light, which is actually on the lower end of what some interstellar mission concepts require, that same dust grain carries a kinetic energy roughly equivalent to a 100-kilogram person running at 13 kilometers per second. Or, to put it another way, the energy of a 10-gram bullet traveling at 1,500 kilometers per second. All of that energy delivered in an instant to a single microscopic point on the surface of your spacecraft. At those speeds, dust grains don't scratch the hull. They don't leave a dent. They explode. The impact is so energetic that the grain vaporizes instantly and blasts a tiny but deep crater into whatever material it hits, like a high-powered drill press working at a molecular level. And over the 4.2 light-years between here and Proxima Centauri, your spacecraft sweeps through a volume of space that contains billions upon billions of these grains per square meter of forward surface. The cumulative effect is erosion, relentless, unavoidable, physical erosion of the front of your spacecraft, eating through whatever shielding you've built, millimeter by millimeter, over the decades of the journey. And there's a deeper uncertainty buried underneath all of this that almost nobody talks about, one that genuinely keeps physicists uncomfortable. We understand the grain sizes we can measure. We have data on the microscopic dust, but the interstellar medium almost certainly also contains larger objects, chunks of ancient ice, fragments of long-dead comets, debris from collisions that happened billions of years ago in star systems we've never observed. Objects that are far too small to detect with any telescope, but far too large to survive a collision with at relativistic speeds. We simply don't know how common these objects are, We can't survey them. We have no catalogue of the hazards lurking between the stars. It's a bit like planning a road trip across a continent, but only knowing there's a road, having no idea whether that road is clear, flooded, or buried under a landslide somewhere along the way. So what can we do about it? How do you shield a spacecraft from this kind of punishment? The concept that gets the most serious attention is a forward shield, a sacrificial layer of material placed at the very front of the spacecraft, designed to absorb the brunt of the particle bombardment and dust impacts. You'd use dense, tough materials with the ability to spread the energy of impacts across as large an area as possible, preventing individual hits from punching all the way through to the sensitive instruments behind. For the breakthrough Starshot concept, with its gram-scale probes, this created a genuinely vicious design problem. The whole point of the mission was to make the spacecraft almost impossibly light, a few grams, including the sail, the instruments, the communications equipment, everything. But a meaningful radiation and dust shield adds mass, sometimes a lot of mass, and every gram of mass you add to the spacecraft is a gram that requires enormously more laser energy to accelerate to the target speed. The shield eats into the mass budget, which forces you to shrink everything else, which makes the shield relatively larger, which adds more mass. A circular problem with no clean solution. Published engineering analyses of the Starshot concept acknowledged this directly. Even a frontal shield of a few hundred grams, which sounds trivial, would dramatically change the energy requirements for the laser array and potentially make an already extraordinarily expensive project even more costly and complex. And then there's cosmic radiation itself, the high-energy particles that stream through the galaxy from supernovae, black holes, and other violent astrophysical sources. These are separate from the interstellar medium entirely. They're not the local hydrogen drifting in the dark. They're high-velocity particles accelerated by some of the most powerful engines in the universe, and they come from every direction, not just the forward face of your spacecraft. Shielding against radiation coming from the front is hard enough. Building a spacecraft that's protected on all sides against galactic cosmic rays for 2 decades of continuous flight pushes the engineering problem into territory that has no satisfying answer yet. Now, to be completely fair, and this is something this channel will always insist on, none of this means interstellar travel is forever impossible. Physics doesn't say that. What physics says is that these are real, serious, unsolved engineering challenges that would need to be addressed before any physical mission to another star could succeed. The interstellar medium is a gauntlet, not a wall. It's a problem to be solved, not a fundamental law forbidding the journey. But the solutions aren't here yet. And in the meantime, every new layer of difficulty we uncover, the distance, the flaring star at the destination, the radiation and dust in between, adds weight to the central argument of this video. The journey to Proxima Centauri is worse than most people think, not because the universe is cruel, but because the universe is honest and it hands out challenges on a scale that matches its own size. There's something almost humbling about that. We are creatures who built civilizations on a rocky world orbiting an ordinary star, and we have the audacity to look at the nearest other star and say, we want to go there. That impulse is one of the most fundamentally human things about us. The cosmos doesn't make it easy, but the fact that we're even asking the question, even mapping out the obstacles, even calculating the radiation doses and the dust grain impacts across 4 light-years of cold, dark space, that itself is astonishing. We are stardust asking questions about the stars. But here's what's genuinely fascinating, and this is something the headlines almost never get to. We've been building something that might be our best answer to all of this. Not a rocket, not a laser sail, something completely different. a way to study Proxima Centauri and its planets without sending anything there at all, a tool so powerful that it could, in theory, let us see the surface of a planet 4 light-years away with more detail than a flyby probe ever could, and it's already out there, waiting for us to use it. Here's an idea so strange, so counterintuitive, that when you first hear it, it sounds less like a scientific proposal and more like something out of science fiction. And yet it's completely real, grounded in Einstein's general theory of relativity, actively studied by researchers at NASA's Jet Propulsion Laboratory, and it could, potentially, change everything about how we think of reaching the stars. What if we didn't need to send a spacecraft to Proxima Centauri at all? What if we could study its planets in extraordinary detail, see their continents, their oceans, their atmospheric chemistry, maybe even signs of life on their surfaces, without traveling a single kilometer beyond our own solar system? What if the most powerful telescope humanity could ever build is already out there, already assembled, already waiting, and it's been waiting for 4.5 billion years? That telescope is our sun. Let me explain, because this concept deserves to be understood properly. Einstein's general theory of relativity tells us that mass warps the fabric of space-time around it. The more massive an object is, the more dramatically it bends the space in its vicinity. And one of the consequences of that warping is that light, which travels through space-time, doesn't travel in perfectly straight lines when it passes close to a massive object. It curves, it bends, it follows the contours of the warped space around it. This is the principle behind gravitational lensing, and astronomers have been using it for decades. When a distant galaxy sits behind a closer, massive galaxy cluster, the cluster's gravity bends the light from the distant galaxy, focusing it and amplifying it in ways that allow us to see things we'd never be able to see otherwise. Sometimes the light wraps so perfectly around the foreground mass that it forms a complete ring, a phenomenon called an Einstein ring, a halo of focused light from a source directly behind the lens. It's one of the most visually striking predictions of general relativity. And it's not just a curiosity, it's a tool, a real, usable, scientific instrument made entirely of gravity and space-time. Now here's where it gets extraordinary. Our sun is massive, not the most massive star in the galaxy, not even close by stellar standards. But it's massive enough that the gravity it exerts bends light, passing near it with significant force. And when physicists worked out the geometry of how that bending works, they discovered something remarkable. All the light from a source directly behind the sun, bent by the sun's gravity on all sides, converges, focuses, into a line extending outward from the other side of the sun, a focal line extending from a minimum distance of roughly 550 astronomical units out into deep space. 1 astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. 550 astronomical units is roughly 82 billion kilometers from the Sun. In terms of our solar system, that's an enormous distance, about 4 times as far as the Voyager probes have traveled in nearly 50 years of flight. It's deep space, well beyond the Kuiper Belt. But here's what waits at that focal line. If you position a telescope somewhere along that line, anywhere beyond that 550 astronomical unit threshold, and you point it back toward the sun with a coronagraph to block the sun's blinding glare, the sun's gravity will have focused and amplified the light from any object directly behind it. Not a little. By a factor of roughly 100 billion, that number is not a typo, 100 billion times amplification. According to work done by physicist Slava Turishev at NASA's Jet Propulsion Laboratory, who led a comprehensive study of this concept under NASA's Innovative Advanced Concepts program, the solar gravitational lens is the only currently known method capable of directly imaging the surface features of an exoplanet. Nothing else we've ever conceived of or built even comes close, and the resolution it could achieve is staggering. Turyshev and his collaborator Victor Toth ran simulations of what this instrument could actually show us. They modeled what Earth itself would look like if it were at the distance of Proxima Centauri, 4.24 light-years away, and observed through the solar gravitational lens. The result was an image with a resolution of 1024 by 1024 pixels, an image in which you could clearly make out the outline of continents, the contrast between ocean and land, the swirling patterns of cloud cover. In one of their simulations, the western coast of North America was clearly identifiable. Let that sink in for a moment. From over 4 light-years away, using our own sun as a lens, we could potentially see a coastline on another planet, and if we applied this to Proxima Centauri B, the actual, real target that sits in that star's orbit 4 light-years from here, we could in principle image its surface with enough detail to detect the presence of large bodies of water, to map the distribution of whatever passes for land, to study its atmosphere with spectroscopic instruments that could pick out the chemical fingerprints of oxygen, methane, carbon dioxide, or ozone. The same signatures that on Earth are produced by life. We could potentially answer the question of whether Proxima B is inhabited, not by flying a spacecraft there, but by repositioning a telescope to the outer edges of our own solar system. NASA confirmed in a Phase 2 study that a mission carrying a meter-class telescope with a solar coronagraph, positioned beyond 547.6 astronomical units, would be capable of directly imaging a habitable, Earth-like exoplanet in our stellar neighborhood. The science is not speculative. The physics is verified. The question is purely one of engineering and will. So how do you get a spacecraft to 550 astronomical units? This is where another piece of elegant physics enters the picture. The same sun that serves as our gravitational lens also powers the answer to how we get there. Solar sails, spacecraft that use the pressure of sunlight itself pushing against enormous gossamer-thin reflective surfaces, can, when deployed at close range to the sun, achieve remarkable velocities. The closer to the sun you deploy the sail at its full size, the more momentum the sunlight transfers to the spacecraft, and the faster you go. JPL mission designs for what they're calling the Solar Gravity Lens Focal Mission envision spacecraft making a close solar pass, potentially dipping as near as a few tenths of an astronomical unit from the sun's surface and deploying their sails at the moment of maximum solar flux, effectively using the sun as both a slingshot and a light source simultaneously. The projected travel time to reach the focal region, based on work published in the journal Experimental Astronomy and discussed by researchers at Centauri Dreams, is roughly 25 years. For a mission to the focal line, not to another star. 25 years to position a relatively small spacecraft, perhaps a 50-kilogram microsat, at a location where our own sun does the observational heavy lifting. 25 years versus the tens of thousands of years it would take any current spacecraft to reach Proxima Centauri itself. But let's be honest about the challenges, because this channel doesn't deal in glossy optimism without the fine print. Reaching the focal line is only the beginning of the imaging process. Once there, the spacecraft doesn't take a single snapshot. The image that the sun focuses isn't projected neatly onto a small screen. It's spread across an enormous area, a cylinder of light more than a kilometer wide. To reconstruct a full image of the target planet, the spacecraft has to maneuver within that cylinder, measuring the brightness pixel by pixel repeatedly over what could be years of observation, all while the planet is orbiting its star. The star is moving through space, and the sun itself is not perfectly stationary. The sun also isn't a perfect lens. Spherical aberrations, astigmatism, and the interfering light of the solar corona, all introduce noise that has to be corrected through a coronagraph and sophisticated image reconstruction algorithms. It's an exquisite engineering challenge, not an insurmountable one, researchers believe, but one that requires significant development. And there's the question of communication. A spacecraft at 500 or 600 astronomical units is far beyond the range of any current deep space communication system operating at conventional data rates. New technologies for transmitting large volumes of data across those distances, possibly using laser communication, would need to be developed and proven, as Forbes reported in late 2025. Researchers both in the United States and Europe are actively working on this concept. The European group, led by the University of Pisa in Italy, calls their version the Curved Space Telescope. They share the same fundamental physics, the same astonishing amplification factor, and the same conviction that the solar gravitational lens represents the most transformative observatory humanity has ever conceived. If it works, and the physics says it should, the implications extend far beyond just Proxima Centauri. The focal line isn't aimed at a single star. By repositioning the spacecraft to different points within the image cylinder, or by launching multiple spacecraft in different directions, you could, in principle, image exoplanets around dozens of nearby stars. Researchers involved in the JPL concept have suggested that for the cost of a single large space telescope, you could potentially send multiple spacecraft out to study a range of planetary systems, each one using the sun's gravity to deliver image quality no manufactured telescope of any conceivable size could match. There is something profoundly beautiful about this idea. We spent centuries building bigger and bigger telescopes, lenses the size of rooms, mirrors the size of swimming pools, orbiting observatories above Earth's blurring atmosphere, and all of that progress, as extraordinary as it has been, still leaves us squinting at pixels too small to resolve the surface of a world around even the nearest star. Then someone looked up at the sun, the very thing that has defined life on this planet since its beginning, and realized it had been patiently waiting all along to show us the universe in its full clarity. If only we were clever enough to use it properly. We are stardust that built instruments, but perhaps the greatest instrument of all was never built by human hands. Still, and this is the tension that makes this whole topic so compelling, the solar gravitational lens doesn't solve the problem of actually going there. It can show us what's on the surface of Proxima B. It can tell us whether the atmosphere contains signatures of life, but it can't bring us there. It can't let us walk on those shores, breathe that air, or confirm with our own presence whether what we're seeing from 500 astronomical units away is what we think it is. And the desire to go, that deeply human, almost irrational impulse to not just observe but to arrive, hasn't gone away. It never will. Which is why the smartest minds in aerospace engineering and theoretical physics haven't stopped thinking about propulsion. And some of the ideas they've been developing operate on principles so different from anything we've launched before that they deserve their own conversation entirely. Because it turns out there's a propulsion concept that doesn't need fuel the way we think of fuel, doesn't need a rocket engine, doesn't need antimatter or nuclear reactors. It uses something we've already demonstrated works and scales, at least theoretically, to the velocities we'd actually need to reach another star. Let's talk about going fast, not highway fast, not jet fast, not even rocket fast in the way we usually mean it. We're talking about a completely different category of speed, the kind of speed that makes everything humanity has ever launched into space look like it's standing still. The kind of speed that, if we ever achieve it, will represent the single greatest leap in the history of transportation, not just since the Wright brothers, not just since the first steam engine, since the first human being lashed two logs together and pushed off from a riverbank. To reach Proxima Centauri in any time frame that a living human could personally witness, let's say within a single human lifetime of 70 or 80 years, you'd need to travel at somewhere between 5 and 20% of the speed of light. The speed of light is approximately 299,792 kilometers per second. 5% of that is roughly 14,989,000 kilometers per second. 20% is almost 60 million kilometers per second. For context, the fastest spacecraft ever launched by humanity was the Parker Solar Probe, which in late 2024 reached a top speed of around 690 kilometers per second on its closest approach to the Sun. That is extraordinary by any normal measure. It is also, relative to what we need for interstellar travel, heartbreakingly slow. At that speed, reaching Proxima Centauri would take roughly 185,000 years. So the question that serious researchers have been wrestling with for decades is not whether we can do better than chemical rockets. Obviously we can, and we must. The question is how much better, with what technology, at what cost, and with what trade-offs. And the answers are fascinating, sobering, and sometimes both at once. Let's start with the concept that gets the most media attention, the most serious institutional backing, and arguably the most elegant physics behind it: laser-pushed sails. The basic idea has been around since the 1960s, when physicist Robert Forward, one of the true visionaries of interstellar propulsion, first wrote seriously about using directed energy to accelerate a spacecraft. But it was the announcement of breakthrough Starshot in 2016 that brought the concept into public consciousness in a dramatic way. Backed by $100 million in seed funding and supported by some of the most prominent names in science, Starshot proposed something genuinely audacious: an array of ground-based lasers, collectively producing around 100 gigawatts of power, focused on an extraordinarily thin, lightweight sail attached to a gram-scale spacecraft, and accelerating that tiny probe to 20% of the speed of light in a matter of minutes, 20% of the speed of light. In minutes, the physics is sound. Light exerts pressure. When photons bounce off a reflective surface, they impart a tiny amount of momentum to that surface. It's a real, measurable, experimentally verified effect. Solar sails, spacecraft that use sunlight itself as their propellant-free thruster, have already been demonstrated in space. Japan's Icaro spacecraft did exactly that in 2010, becoming the first spacecraft to successfully demonstrate solar sail propulsion in deep space. NASA's NanoSail D and the Planetary Society's LightSail 2 have since confirmed the principle works. But sunlight is diffuse and relatively weak. To get to interstellar velocities, you need to replace the gentle push of ambient sunlight with an enormously concentrated, coherent beam of laser light. Point it at a sail that reflects as close to 100% of the incoming photons as possible, and you can dump a staggering amount of momentum into even a very small object in a very short time. The engineering challenges, however, are where the elegance of the physics runs headlong into the brutality of reality. Challenge 1. The laser array itself. 100 gigawatts is not a power level that exists in any human installation today. The entire electricity generating capacity of the United Kingdom is roughly 75 gigawatts. Starshot's laser array would need to exceed that briefly in a pulsed burst, directed with extraordinary precision from the ground through the atmosphere to a target that is getting smaller in the sky with every passing second. Building and powering this array has been estimated to cost tens of billions of dollars at minimum, and possibly significantly more. The adaptive optics system required to compensate for atmospheric turbulence at that power level would itself be a formidable engineering project with no clear existing roadmap. Challenge 2. The sail itself. For the concept to work, the sail needs to be almost unimaginably thin, on the order of a few hundred atoms thick, while also reflecting the incoming laser light with near-perfect efficiency and surviving the thermal load of having 100 gigawatts focused on it for several minutes. A sail that absorbs even a fraction of a % of that energy would heat up catastrophically and vaporize before the spacecraft reached its target speed. Researchers at UC Santa Barbara and elsewhere have been investigating materials like silicon nitride and other nanoscale films as candidates, but fabricating such a sail at useful scales, meters across, grams in mass, remains a manufacturing challenge without precedent. Challenge 3. Pointing. As the spacecraft accelerates away, the angular size of the sail as seen from the laser array shrinks rapidly. Within the first few seconds of acceleration, the beam needs to track and remain precisely centered on a target that is moving at a significant fraction of the speed of light and getting farther away by the millisecond. The tolerance for error is essentially zero. A slight misalignment and the sail tumbles, tears, or simply stops accelerating. And then there's the problem we touched on in the last section, the interstellar medium. Even a gram-scale sail traveling at 20% of the speed of light faces the radiation and dust hazards we discussed. At those velocities, the forward face of the spacecraft, however small, is being continuously bombarded by particles energetic enough to degrade materials in ways that are genuinely difficult to model accurately over 4 light-years of flight. Starshot scientists are not unaware of these problems. Published analyses from the project's working groups acknowledge every one of them as open engineering questions. The optimistic view is that all of them are solvable in principle, and that the 20 or 30-year development timeline the project has outlined is realistic. The skeptical view, held by a number of respected physicists, is that several of these challenges may be far harder than the public announcements suggest, and that the cost and complexity of a real mission would dwarf even the most ambitious current estimates. But laser sails aren't the only serious option on the table. Let's talk about nuclear pulse propulsion, a concept so powerful and so controversial that it was actually studied intensively by the United States government in the 1950s and 60s before being quietly shelved, not because it didn't work, but because it worked in a way that made international treaties extremely uncomfortable. The concept is called Project Orion, and its core idea is one of the most audacious things ever seriously proposed in aerospace engineering. You build a spacecraft with a thick, heavily engineered pusher plate at the back. You eject a series of small nuclear devices, essentially miniature atomic bombs, behind the ship one at a time. Each bomb detonates. The explosion's plasma and radiation hits the pusher plate. The plate is pushed forward. The spacecraft accelerates. You detonate a nuclear bomb behind your spaceship. Then you do it again. Thousands of times. This sounds insane. It also, according to the physicists who studied it, including Freeman Dyson, one of the most brilliant theoretical physicists of the 20th century, actually works. The energy density of nuclear explosions is so far beyond any chemical propellant that an Orion-style spacecraft could, in principle, reach velocities of several % of the speed of light, given enough bombs and a large enough ship. Dyson himself calculated that a reasonable-sized Orion spacecraft could potentially reach Proxima Centauri in as little as 130 years, not a human lifetime, but a generational timescale that isn't entirely beyond imagination. The problems are not primarily technical, they are legal, political, and environmental. The Partial Test Ban Treaty of 1963, signed by the United States, the Soviet Union, and the United Kingdom, prohibits nuclear detonations in space. Any Orion-style mission would require either renegotiating or abandoning international arms control agreements that have been foundational to nuclear non-proliferation efforts for over 60 years. Beyond the legal question, launching a spacecraft on nuclear explosions from within Earth's atmosphere or even from orbit would distribute radioactive fallout across the planet in ways that would be environmentally catastrophic. An Orion mission launched from deep space, where there is no biosphere to contaminate, sidesteps the environmental issue, but not the treaty issue, and the sheer logistics of building, fueling, and deploying a spacecraft that carries thousands of nuclear devices to orbit is itself a challenge of staggering scale. A more refined descendant of the Orion concept is nuclear pulse propulsion using controlled thermonuclear fusion rather than fission bombs, a concept explored in the 1970s under Project Daedalus, a study conducted by the British Interplanetary Society. Daedalus proposed using tiny pellets of deuterium and helium-3 ignited by electron beams at a rate of 250 pulses per second to generate a continuous series of microfusion explosions driving the spacecraft forward. The projected result was a vehicle capable of reaching 12% of the speed of light, enough to reach Proxima Centauri in roughly 36 years. There's a significant catch, which the Daedalus study acknowledged openly. Helium-3, the preferred fuel, is extraordinarily rare on Earth. The study proposed harvesting it from the atmosphere of Jupiter, a mining operation that doesn't exist and that would require decades of technological development to make feasible. Fusion ignition itself, despite decades of ongoing research, still hasn't been achieved at the net energy positive levels required to make it a practical propellant, let alone a pulse drive at those firing rates. And then there's antimatter. Antimatter propulsion is, in pure physics terms, the most efficient reaction drive conceivable. When matter and antimatter meet, they annihilate each other completely, converting their entire combined mass into pure energy according to Einstein's famous equation. The energy yield per kilogram of fuel is roughly 10 billion times greater than the best chemical rocket and thousands of times more than even nuclear fission. A matter-antimatter drive, in principle, could accelerate a spacecraft to a substantial fraction of the speed of light. In practice, there are problems that currently place antimatter propulsion firmly in the realm of theoretical interest rather than imminent engineering. First, production. CERN's particle accelerators produce antiprotons at a rate of around 10 billion per hour. That sounds like a lot. It isn't. 10 billion antiprotons has a combined mass of around 17 femtograms, 17 millionths of a billionth of a gram. A useful interstellar mission would need grams to kilograms of antimatter. At CERN's current production rate, accumulating a single gram of antiprotons would take approximately 10 million years. Published estimates suggest that producing antimatter in the quantities needed for propulsion is off by many orders of magnitude from anything currently achievable, and no known physics suggests a shortcut to dramatically faster production. Second, storage. Antimatter annihilates instantly on contact with ordinary matter, including the walls of any container you try to store it in. Keeping antimatter isolated from ordinary matter requires powerful magnetic fields in devices called penning traps. Current technology can store a few thousand antiprotons at once. Scaling that to grams or kilograms of stored antimatter is an unsolved engineering problem of enormous complexity. Third, cost. The estimated cost to produce a single gram of antimatter using current methods has been estimated at tens of trillions of dollars. That figure would need to drop by many orders of magnitude for antimatter propulsion to become practical in any economic sense. None of this makes antimatter propulsion a fantasy. Physics doesn't prohibit it. But physics being silent isn't the same as engineering being ready, and right now, the gap between the concept and the capability is vast. So where does this leave us? We have laser sails that require engineering feats without precedent and face hazards across the journey that haven't been fully solved. We have nuclear pulse drives powerful enough in principle but entangled in legal, political, and logistical nightmares. We have fusion drives that depend on fuels we can't yet produce at scale and ignition methods we haven't fully demonstrated. And we have antimatter engines that are theoretically perfect and practically nearly impossible with current technology. It's a humbling inventory. The universe isn't telling us we can never get there, but it is telling us, quite firmly, that the path involves a series of problems, each of which would individually be among the grandest engineering projects in human history. Stacked on top of each other, across the decades it would take to develop each one, the sheer magnitude of the undertaking begins to come into focus. And yet, and here is the tension that makes this topic so endlessly compelling, every single one of these concepts is grounded in verified physics. None of them requires the discovery of new laws of nature. None of them invokes warp drives or wormholes or exotic matter with negative mass. They are all, in principle, achievable with the universe as it actually is. The challenges are enormous. They are not magic. But here's something that doesn't get discussed nearly enough when people talk about interstellar propulsion. Even if you solve every single one of the engineering problems, even if you build the laser array, or perfect fusion pulse ignition, or find a way to store grams of antimatter safely, you still haven't addressed a challenge that might be the most profound of all, one that has nothing to do with rockets or sails or nuclear physics. What happens to the people inside? Because the journey to Proxima Centauri, even at the most optimistic speeds realistic physics allows, is still going to take years or decades, and human beings, fragile, social, psychologically complex human beings, have never been isolated from their species for anywhere remotely close to that long. What does that do to a person? What does it do to a crew? Let's get personal for a moment. Everything we've talked about so far has been about the universe outside the spacecraft, the distance, the radiation, the interstellar medium, the propulsion systems, the physics, and all of that is genuinely hard. Some of the hardest engineering and science problems our species has ever confronted. But there's another set of problems that lives inside the hull, behind the shielding, in the cabins and corridors and common areas of whatever vessel we eventually send toward another star. And those problems don't respond to better materials or more powerful lasers or refined calculations. They respond, or sometimes fail to respond, to something far more unpredictable than physics. They respond to people. Human beings are not designed for space. We say that casually sometimes, almost as a throwaway observation, but it's worth sitting with for a moment and really letting it land. Every single system in your body, your cardiovascular system, your skeletal structure, your immune system, your sense of balance, your circadian rhythms, your digestive system, your mental health, every one of them evolved under very specific conditions. One gravity, a 24-hour day-night cycle driven by a star 8 light minutes away, a thick atmosphere filtering radiation, a planet full of other human beings, food that grows in soil, air that smells like something. Remove any of those conditions and the body begins to struggle. Remove most of them simultaneously, which is exactly what an interstellar voyage would do, and you're running an experiment on human physiology that we've only barely begun to understand, and the early results are not entirely reassuring. Let's start with the body. The most extensively studied effect of long-duration spaceflight on human health comes from low Earth orbit, specifically from the International Space Station, where astronauts have been living and working continuously since the year 2000. The longest single stays have stretched to over a year. Russian cosmonaut Valery Polyakov holds the record for the longest continuous stay in space at 437 days, set back in 1994 and 1995. More recently, American astronaut Frank Rubio spent 371 consecutive days aboard the ISS after his return capsule was damaged. What those long stays have taught us about the human body in microgravity is a catalogue of challenges that grows more detailed and more concerning the longer the missions last. Bone density loss. In the absence of the mechanical loading that gravity places on your skeleton every time you take a step, your bones begin to shed calcium. The cells responsible for building new bone tissue, osteoblasts, become less active. The cells responsible for breaking down old bone, osteoclasts, remain at normal activity levels. The result is a net loss of bone mass that, without rigorous countermeasures, can reach 1 to 2% per month in load-bearing bones like the hip and spine. Over a year, that's the kind of bone density loss you'd associate with severe osteoporosis in an elderly person. The countermeasure, 2 or more hours of resistive exercise every single day, slows but doesn't fully stop the process, and it has to be maintained relentlessly. Miss a few days, and the degradation accelerates. On a journey to Proxima Centauri at 20% of the speed of light, roughly 20 years of flight time, the cumulative skeletal challenge is something we genuinely don't know how to fully address with current technology. Rotating habitat sections to generate artificial gravity are one proposed solution, and they would help enormously. But adding a rotating segment to an already technically demanding spacecraft adds mass, complexity, and failure points. Muscle atrophy follows a similar pattern. Without gravity demanding that your muscles constantly support your own weight, they begin to waste. The body, in its brutal efficiency, interprets unused muscle as an unnecessary metabolic cost and begins dismantling it. Astronauts returning from 6-month missions describe difficulty walking for days or weeks afterward. Returning from a multi-year journey, the rehabilitation period could be substantially longer, assuming the destination environment has gravity to rehabilitate in. Cardiovascular changes are subtler but potentially more serious over very long timescales. In microgravity, fluid shifts toward the upper body and head. The heart, no longer working against gravity to pump blood upward, becomes slightly smaller and less efficient over time. A process called cardiac atrophy, blood pressure regulation becomes disrupted. Some astronauts develop a condition called spaceflight-associated neuroocular syndrome, SANS, in which the pressure of fluid accumulating around the optic nerve flattens the back of the eyeball, permanently altering vision. As of the latest data published by NASA and reviewed by researchers at the Baylor College of Medicine, a significant fraction of long-duration astronauts experience measurable vision changes, and in some cases those changes have not fully reversed after return to Earth. SANS is one of the most actively researched concerns in human spaceflight medicine right now, because unlike bone loss, which responds to exercise, there is currently no confirmed countermeasure. The mechanism is understood in broad terms, but how to prevent the fluid pressure buildup over a multi-year mission is an open research question. On an interstellar voyage, there's no option to return early if symptoms worsen, and then there's radiation. We touched on interstellar radiation in the context of the journey through space itself. The galactic cosmic rays and solar energetic particles that bombard anything beyond Earth's protective magnetosphere. But it's worth going deeper on what that radiation actually does to the people inside the spacecraft, because the biology here is striking. Galactic cosmic rays are high-energy charged particles, mostly protons, but including heavy ions from elements like iron, moving at close to the speed of light. They punch straight through the walls of a spacecraft and straight through the human body. Unlike the X-rays used in medical imaging, which deposit most of their energy fairly quickly as they pass through tissue. Heavy cosmic ray ions travel deeply into the body before depositing their energy, leaving a trail of ionized, damaged cells along their path. The immediate concern is cancer risk. Every cosmic ray that passes through your body has some probability of damaging the DNA in a cell in a way that initiates malignant transformation. NASA's current radiation exposure limits for astronauts are set to keep the lifetime increased cancer risk below 3%. The radiation dose accumulated on a journey to Proxima Centauri, even with shielding, would almost certainly exceed those limits by a substantial margin based on current models published in journals like Nature and Radiation Research. How substantially depends on the shielding design, the mission duration, and the state of the solar cycle during the journey. But the numbers are not comfortable. What's been even more surprising to researchers is the effect of cosmic radiation on the brain. Studies conducted on mice exposed to simulated cosmic ray doses, published in scientific journals including Science Advances, have found significant cognitive impairments, memory problems, reduced ability to learn new tasks, anxiety-related behavior changes, changes in the structure of neural dendrites, the branching extensions through which nerve cells communicate. The brain, it turns out, is not just at risk from radiation-induced tumors. The neural tissue itself can be directly damaged in ways that affect thinking, memory, and emotional regulation. This research is still developing, and extrapolating from mice to humans carries real uncertainty. But the directional finding that chronic cosmic radiation exposure may impair cognitive function is concerning enough that it's now a central area of research for any agency seriously planning long-duration deep space missions. NASA's Artemis program, which intends to send astronauts to the moon for extended stays, is partly motivated by the desire to understand these effects at closer range before attempting anything like a Mars mission, let alone anything beyond. Now let's talk about something that doesn't show up on blood tests or bone density scans, but may ultimately matter just as much. Let's talk about the mind. The psychological literature on isolation and confinement, drawn from research on Antarctic winter-over cruise, submarine deployments, polar expeditions, and dedicated isolation studies conducted by space agencies, paints a picture of what happens to human beings when they are cut off from the broader social world for extended periods. And the picture has some very consistent features. Irritability tends to increase over time, especially within small groups where the same personalities interact day after day with no opportunity for escape or refresh. What researchers call interpersonal friction. These small accumulated frustrations of living in close quarters with the same people indefinitely compounds in ways that are difficult to model on short timescales but become significant over months and years. Documented cases from Antarctic overwinter stations where crews of a dozen or so people spend 8 months or more in complete isolation during the polar winter show patterns of social withdrawal, increased conflict, and in some cases what researchers describe as a third-quarter phenomenon, a notable psychological low point around 3/4 of the way through a fixed-duration mission, as the crew simultaneously confronts the accumulated stress of the mission so far and the still significant distance remaining to its end on a journey to another star. There is no fixed end point in the way an Antarctic winter has one. The duration is not months but years. The distance from any other human being, any other member of the species, grows continuously until it reaches a scale that has no precedent in human experience. At some point in the outbound journey, Earth becomes just a point of light, then it becomes invisible to the naked eye. Then the sun itself begins to dim to something that merely resembles a bright star rather than a star that is yours. No human being has ever experienced that. We have no data on what it does to a person. We have theoretical frameworks from psychology, extrapolations from isolation studies, informed speculation from researchers who study the condition. But the experience itself, being the farthest human being from Earth in the history of the species, surrounded by a small group of colleagues, in a vessel that cannot turn back, is genuinely unprecedented. And unprecedented experiences have a way of producing unexpected outcomes. There have been structured attempts to simulate this. The Mars 500 study, conducted jointly by the European Space Agency and Russia's Institute for Biomedical Problems from 2010 to 2011, confined 6 volunteers inside a sealed facility in Moscow for 520 days, roughly the estimated duration of a round-trip Mars mission. The results were instructive. Several crew members developed what the researchers described as sedentary behavior patterns, sleeping more, moving less, becoming increasingly passive over time. One participant developed a marked disruption of their sleep-wake cycle, eventually shifting to a 25-hour internal day that drifted continuously out of sync with the external world. Interpersonal dynamics became strained, motivational issues emerged in the later stages, and Mars is next door compared to Proxima Centauri. There's another dimension to the psychological challenge that rarely gets discussed openly, and it's one of the most philosophically significant aspects of the entire enterprise. Communication delay. Right now, if an astronaut on the International Space Station wants to speak to a family member on the ground, they can. The signal travels the 400 kilometers or so to Earth's surface in a fraction of a millisecond, essentially real-time. A Mars mission at average distance introduces a communication delay of around 12 minutes each way, long enough to be frustrating, but still within a framework where conversation is possible, just asynchronous. You send a message, you wait 24 minutes for a reply, you have a conversation measured in hours rather than seconds. At the distance of Proxima Centauri, the communication delay is 4.24 years each way. You send a message home. Your child, who was 7 years old when you left, is 11 by the time your words arrive. Their reply reaches you when they are 15. If you left a partner behind on Earth, any exchange of words takes 8.5 years round trip, not a conversation, not even really correspondence. Something closer to sending messages in a bottle across an ocean, except the ocean is interstellar space and the bottle travels at the speed of light. The crew of an interstellar mission would, by the nature of physics, become completely severed from the living, evolving, changing civilization they came from. The Earth they left, and the Earth they might eventually hear back from, are, in a meaningful sense, different Earths. Political structures would change, languages would shift, technologies would transform. The people they knew would age and eventually die, and all of that would happen in silence, relayed across the years in packets of electromagnetic radiation that arrive years apart. There's a word for the feeling that some researchers have started to use in the context of interstellar psychology, borrowed from geography, solastalgia. It was originally coined to describe the grief people feel when their home environment is irreversibly changed. Applied to an interstellar crew, it takes on a new and piercing meaning. The home you left doesn't just feel far away. In a very real sense, it has moved on without you. It has become a different place, inhabited by different versions of the people you knew, shaped by events you couldn't participate in or even observe. How do you prepare a human being for that? How do you select for the psychological profile that could withstand not just the isolation and the confinement and the physical challenges, but the grief of watching your own civilization become, year by year, a stranger? We don't have a complete answer. What we have are research programs, theoretical frameworks, proposals for crew selection criteria, and the accumulated wisdom of people who've lived through months in Antarctic isolation or months aboard a space station. It's a foundation, but the gap between that foundation and what an interstellar mission would actually demand is one of the most profound and underappreciated challenges in the entire enterprise. And we haven't even gotten to the question of what happens if the mission isn't a one-way trip for a single generation. What if reaching Proxima Centauri requires sending not one crew, but an entire self-sustaining community? What if the timescales involved mean that the people who arrive at Proxima Centauri aren't the people who left Earth at all, but their children or their grandchildren, born and raised entirely within the confines of a spacecraft, never having seen a planet or felt wind on their skin or stood under an open sky? The concept is called a generation ship, and the questions it raises aren't just biological or psychological, they're ethical, political, and philosophical in ways that cut right to the heart of what we think it means to be human, to have rights, to make choices, and to live a meaningful life. That's exactly where we're going now, because the generation ship concept forces us to ask questions that don't have easy answers. Questions about the children who would be born into a mission they never chose, about governance and power in an isolated community with no outside authority, about what happens when people disagree or dissent, or simply want something different from the life they were handed at birth, about what kind of society forms when your entire world is a cylinder of metal a few hundred meters long, and the nearest alternative reality is years of light away in every direction. The physics of interstellar travel is hard, the engineering is harder, but the ethics of generation ships might be the hardest question of all. If you are still watching, don't forget to subscribe and give this video a like. Every video on this channel is designed to give you that feeling of standing at the absolute edge of what humanity knows. Let's imagine a child. She's 8 years old. She's never seen rain. She's never felt grass under her feet. She's never looked up at a sky, not a real one, not one that goes on forever in every direction, filled with weather and birds, and the particular quality of light that changes through the day as a star moves across it. She's never been in a room that she couldn't cross in 30 seconds. She has never met a stranger. She knows every face in her world, every voice, every personality quirk of every person she will ever encounter in her life, because every person she will ever encounter is already here, already aboard, already part of the same small sealed community she was born into. She didn't choose this. She couldn't have. She was born on the ship. Her parents were born on the ship. Her grandparents were the ones who left Earth, and those grandparents are elderly now, and the stories they tell about open skies and ocean winds and cities full of millions of people feel to her the way ancient mythology feels to us, vivid and compelling and completely unreal. Things that happen to other people in another world that she will never see and can barely imagine. This child is the subject of one of the most uncomfortable ethical debates in the entire field of interstellar travel research. And it's a debate that doesn't get nearly enough airtime in the popular conversation about reaching other stars, because it forces us to confront something most of us would rather set aside. The question of whether we have the right to do this at all. A generation ship, for those unfamiliar with the concept, is exactly what it sounds like. A spacecraft large enough and self-sufficient enough to support a complete human community across multiple generations. The crew that departs Earth is not the crew that arrives at the destination. Depending on the propulsion system and the travel time, it might be their grandchildren, or their great-great-grandchildren, or descendants separated by 10 or 15 generations from the people who made the original decision to go. The logic is compelling. If we can't get to Proxima Centauri in a single human lifetime at achievable speeds, Maybe we stop thinking about the journey as something one person or one crew experiences and start thinking about it the way we think about a cathedral, something built across generations, where the people who lay the foundation never see the spire, but the spire gets built anyway. It's a beautiful idea. It's also, when you examine it carefully, one that raises questions serious enough that a small but growing body of bioethicists, philosophers, and legal scholars have been publishing papers about it for decades, papers that use phrases like reproductive coercion, imposed life plans, and the non-identity problem in ways that are deeply unsettling when applied to the context of space exploration. Let's start with the most fundamental question. The children born aboard a generation ship never consented to the mission. They didn't exist when the decision was made. They are brought into life inside a radically constrained environment with a predetermined destination, a predetermined social structure, and a life trajectory that was decided for them before they were born by people they will never meet. In what meaningful sense are they free? This is not a new philosophical problem. Philosophers have wrestled with the ethics of bringing children into various kinds of constrained circumstances for centuries. Every child born into poverty, or into a culture with rigid social hierarchies, or into a remote community with limited options, is in some sense shaped and limited by circumstances they didn't choose. We don't generally consider that a sufficient reason to prohibit reproduction in difficult circumstances. But a generation ship represents a constraint of a qualitatively different order. It is not merely difficult circumstances, it is a physically sealed world with no exit. A child born aboard cannot decide at 18 that they want to leave and go somewhere else, cannot emigrate, cannot defect, cannot opt out. The walls of their world are absolute in a way that no earthly constraint has ever been, because earthly constraints, however severe, exist within a larger physical reality that a sufficiently determined person can sometimes navigate around or escape. The generation ship offers no such possibility. Philosopher George Dvorsky, writing about the ethics of generation ships, has described this as a form of what he calls existential imprisonment, not in a punitive sense, but in the structural sense that the lives of the shipborne are bounded in a way that removes certain categories of choice entirely. You can make many decisions within your bounded world. You cannot make the decision to leave it. The philosopher Millard Longman and various colleagues in the bioethics literature have framed the question in terms of what's called a life plan. Every person, the argument goes, has some fundamental interest in being able to form and pursue their own life plan, their own vision of what constitutes a good life and how to pursue it. The generation ship doesn't just constrain one or two options, it constrains the entire category of options that involves any world other than the one you were born into. The mission becomes your life plan, whether you endorse it or not. Supporters of the generation ship concept push back on this, and their counter-arguments are worth taking seriously. One response is that no one chooses the circumstances of their birth. Every human being is born into a specific culture, a specific set of material circumstances, a specific language, a specific set of social expectations. The generation ship crew is just a particularly vivid example of a universal human condition. Another response is that the children born aboard the ship will be raised within a community that gives them meaning, belonging, skill, purpose, the things that matter for human flourishing, and that the absence of an exit door doesn't automatically make a life less rich or less worth living. There's something to both of those arguments, but neither fully resolves the discomfort, and the discomfort is worth holding rather than dissolving too quickly. Because once you're on a generation ship, you're committed in a way that no other human endeavor has ever required. The people making the decision to launch are making it not just for themselves, but for everyone who will ever be born aboard that vessel. That is an extraordinary form of power over other people's lives. And history has not been kind to arrangements where one group holds that kind of unilateral power over another. Which brings us to governance. How does a generation ship govern itself? This question has been studied in the context of long-duration spaceflight for decades, and the conclusions are sobering. Small, isolated communities under stress tend toward authoritarianism. This is not a cynical observation, it's a fairly robust finding from the sociology of crisis situations, island communities, and isolated settlements. When resources are limited, when the margin for error is thin, when dissent could theoretically endanger the entire group, there is enormous pressure, structural and social, towards centralized control, conformity, and the suppression of deviation. On a generation ship, the stakes of deviation are not abstract. A single person making a catastrophically bad decision, sabotaging life support, breaching the hull, spreading a pathogen through the enclosed air supply, could kill everyone. The community's survival literally depends on a level of collective coordination and discipline that has no peacetime parallel on Earth. The temptation to enforce that coordination through authoritarian means would be ever present. The institutions and cultural norms that make democracy work on Earth, free press, independent judiciary, the ability to physically leave a community you disagree with, are all absent or radically attenuated. Some researchers have proposed constitutional frameworks for generation ships, documents analogous to national constitutions, drafted before departure, that establish rights, distribute power, create mechanisms for peaceful conflict resolution, and protect individuals from the community's collective pressure. The idea is that you hard-code liberal democratic norms into the ship's founding documents and build institutions to enforce them before the voyage begins, so that the pressure toward authoritarianism has structural resistance built in from the start. It's a reasonable idea. It also assumes that documents and institutions created by one generation will be respected and maintained by subsequent generations who had no part in creating them under circumstances of stress and constraint that the founders couldn't fully anticipate. History's record on constitutions surviving intact under pressure is, to be charitable, mixed. There's a related challenge that touches on genetics and biology rather than politics. For a generation ship community to be genetically viable across multiple generations, to avoid the inbreeding and loss of genetic diversity that plague small isolated populations, researchers have calculated that you need a minimum founding population of somewhere between 160 and several thousand people, depending on whose model you use. A widely cited study published in the journal Acta Astronautica by anthropologist Cameron Smith proposed a minimum viable population of around 10,000 people for a multi-generational interstellar voyage to ensure sufficient genetic diversity and resilience against disease, accidents, and other demographic shocks. 10,000 people. That's not a crew, that's a small town. The spacecraft required to house, feed, provide air and water for, and meaningfully sustain 10,000 human beings across multiple generations would be of a scale that makes every spacecraft ever built look like a toy. The mass, the energy requirements, the agricultural systems, the manufacturing capacity, the medical infrastructure, all of it scales with population in ways that quickly push the engineering requirements into territory that is staggering even by the standards of ambitious interstellar concepts. Smaller founding populations are possible if you supplement biological reproduction with frozen genetic material, sperm, eggs, embryos that can be used to introduce new genetic lineages into the population as needed. This approach has been seriously proposed and has a certain elegant efficiency to it. it also raises its own ethical questions about the instrumentalization of human reproductive material across generations and the social and psychological dynamics of a community that periodically introduces children whose genetic parents are frozen samples from a vault rather than living members of the community. There's one more aspect of the generation ship problem that I want to sit with for a moment, because I think it's the one that cuts deepest philosophically. It's the question of purpose. The founding generation, the people who actually leave Earth, have an obvious purpose. They chose this, they believed in it, they trained for it, worked toward it, gave up whatever they gave up to be part of it. Their commitment is genuine and freely given, and that commitment gives meaning to the extraordinary sacrifices the voyage demands. What about the third generation? The people who grew up hearing stories from grandparents they may barely remember about a blue planet they've never seen, heading toward a star system that is still decades away. Their entire lives will be spent in the middle of the journey, not the departure, not the arrival, not the part of the story that gets remembered or celebrated, just the long, empty middle, the part that goes on, the part that is, in the day-to-day experience of living it, mostly just maintenance and routine, and the particular kind of patience required to pursue a goal you will personally never reach. What does it feel like to be the middle generation? To know that you are, in some cosmic accounting, a means to an end, a biological bridge between the people who made the choice and the people who will reap whatever reward the choice eventually yields. To live your entire life in service of a project that was decided before you were born and won't be completed before you die. These are not unanswerable questions. Human beings have always found meaning in projects larger than themselves, in contributing to things they won't live to see completed. People plant trees in whose shade they'll never sit. Parents sacrifice for children who will outlive them. Civilizations build cathedrals across centuries. There is something deeply human about participating in a story larger than your own lifespan, and many philosophers would argue that this capacity to find meaning in transgenerational projects is one of the most distinctly human things about us. But those examples all happen within a shared civilization, connected to the broader human story. The middle generation of a generation ship is not just making a sacrifice within a shared world. They are the entire world, sealed inside metal, hurtling through a darkness that has no bottom, with no news from home that isn't years old by the time it arrives. Whether that kind of life can be genuinely meaningful, not just tolerable, not just survivable, but actually rich and worthy and worth living on its own terms, is a question that deserves far more honest engagement than it usually gets in the breathless enthusiasm that surrounds interstellar travel discussions. And yet here's what makes this conversation so extraordinary. We are actually having it. As a species, we have arrived at the moment in our history where the question of how to ethically organize an interstellar community is a real question being seriously debated by real scholars in real journals. Not science fiction, not thought experiment for its own sake. Actual preparation for an actual possibility that actual human beings might one day confront. That alone is remarkable. Whatever your conclusions about the ethics, the politics, the psychology, the biology, the fact that we're asking these questions at all means we've come far enough to see the shape of the problem. And seeing the shape of a problem clearly is always, in science as in life, the necessary first step towards solving it. But here's the thing, we've spent 7 parts now exploring why the journey to Proxima Centauri is so much harder than it looks. And every part has uncovered another layer of difficulty, another dimension of the problem that doesn't yield easily to any existing solution. So in part 8, we're going to shift the frame slightly, because there's a question that has been quietly sitting underneath everything we've discussed, and it's time to bring it to the surface. It's the question that some of the most serious researchers in the field are now asking out loud, and the answer they're reaching is surprising, uncomfortable, and maybe the most important thing we'll cover in this entire video. The question is this: given everything we now know about what interstellar travel would actually require, the propulsion, the radiation, the biology, the psychology, the ethics, the generational cost, is sending human beings to another star actually the right goal? Or is it a deeply human impulse that leads us toward the wrong answer to the right question? Let's ask the uncomfortable question, not the question of whether we can go. We've spent 7 parts unpacking that, and the answer is complicated and humbling and full of caveats. The question I want to ask now is different. It's the question that tends to make space enthusiasts shift uncomfortably in their seats, because it challenges something that feels almost sacred: the image of a human being, standing on alien soil, looking up at a foreign sky, planting a flag or a boot print, or simply a presence in a world that has never known one. The question is, why does it have to be a person? This isn't a defeatist question. It isn't a question born of pessimism or a lack of imagination. It's actually the opposite. It's a question born of taking the full scope of our technological trajectory seriously and following it honestly to where it leads. And where it leads, increasingly, is to a conclusion that a growing number of serious researchers in astrobiology, robotics, artificial intelligence, and interstellar studies are reaching independently of each other. The conclusion is this: in the time frame relevant to any realistic interstellar mission, the distinction between a human crew and an artificial one may become far less meaningful than it currently appears, and in some dimensions, it may flip entirely, with artificial systems being not just more practical, but more capable, more resilient, and more likely to successfully complete the mission than biological ones. Let me build this argument carefully, because it deserves to be taken seriously rather than dismissed as either obvious or heretical. Start with what we've established about biological humans in interstellar space. They lose bone density, their muscles atrophy, their cardiovascular systems reorganize in ways that may be permanent, their vision degrades, their brains absorb radiation that may impair cognition over timescales of years. They experience profound psychological stress from isolation and confinement. They require food, water, air, and an enormously complex life support system that has to function without failure for decades. They get sick, they grieve, they conflict with each other, they need sleep. Roughly 1/3 of every single day, unavoidably doing nothing at all in terms of mission-relevant work. And ultimately, in a time frame measured in decades, they die, regardless of any other variable. Every one of those constraints vanishes when you remove the biological crew, a robotic spacecraft, or more precisely, a spacecraft carrying sophisticated artificial intelligence and a suite of scientific instruments, doesn't lose bone density. It doesn't experience radiation-induced cognitive decline or depression or interpersonal friction or the grief of watching Earth's signal grow older and older. It doesn't need to breathe or eat or sleep. It can operate continuously without the metabolic overhead of keeping a biological system alive for as long as its power source holds and its components don't fail. And components, unlike organisms, can be designed with redundancy, multiple backup systems for every critical function in ways that a biological body simply cannot be. The radiation problem doesn't disappear for robotic systems. Electronics are vulnerable to radiation damage too, and hardening spacecraft electronics against the cosmic ray environment of interstellar space is a genuine engineering challenge. But the solutions available to an engineering team designing radiation-hardened electronics are fundamentally more tractable than the solutions available to a team trying to protect a biological brain from the same radiation. You can shield electronics more aggressively because electronics don't need food or air or exercise. You can design in redundant processors that swap in when others are damaged. You can, in principle, design systems that detect and repair radiation damage at the component level. None of those options are available to a biological crew. The communication delay problem, 4.24 years each way to Proxima Centauri, changes character entirely for an autonomous robotic mission. A human crew needs real-time or near-real-time guidance and support from Earth, or at minimum the psychological anchor of being in contact with their home civilization. An artificial system designed for autonomous operation doesn't need that contact to function. It carries its mission parameters and decision-making frameworks internally, executes them without waiting for Earth to respond, and transmits its findings home at whatever cadence its data systems allow. The 8.5-year round-trip communication lag becomes a design parameter rather than a psychological crisis. The mass and energy requirements shrink dramatically. The life support systems disappear entirely. The agricultural systems, the medical bays, the psychological support infrastructure, the generational population management, the ethical frameworks for children born without consent, all of it goes away. What remains is the spacecraft itself, the propulsion system, the instruments, the power source, and the artificial intelligence managing all of it. The mission becomes, in engineering terms, vastly simpler, though still enormously difficult by any absolute measure. Breakthrough Starshot, which we discussed in Part 5, implicitly acknowledges this logic. The gram-scale spacecraft it proposes, sending at 20% of the speed of light, carries no human beings, no life support, no consumables. It carries sensors, a camera, a communication laser, and the electronics to run them. The entire concept is predicated on the recognition that what we actually want from an interstellar mission, data, images, measurements, evidence, can be delivered by a machine at a fraction of the cost and complexity of a crewed mission. Now, there's a counter-argument that I want to take seriously because it's not trivial. The counter-argument is that human presence at another star would mean something that robotic presence simply cannot. That a human being standing on Proxima B, if it turns out to be a world that can support a human being standing on it, would represent something categorically different from a robot doing the same. That the meaning of exploration is inseparable from the experience of the explorer. That data transmitted by a machine is not the same as a human being being there, even if the numbers are identical. This argument has a deep emotional resonance. It's the argument that sends a shiver down your spine when you think about it the right way. And I don't want to dismiss it, because I think it's pointing at something real, something about the irreducible value of direct human experience, of consciousness confronting the cosmos firsthand, of the story of humanity literally extending itself across the stars. But here's the tension. That argument is essentially aesthetic and philosophical rather than scientific. The science, the data, the measurements, the understanding of whether Proxima B has an atmosphere, whether it has water, whether it shows any signs of biology, all of that comes back the same whether a human hand is on the instruments or not. The meaning we attach to human presence is real, but it's meaning we generate. It doesn't live in the data, it lives in us. And if we could generate that meaning some other way, through immersive telepresence, through AI systems sophisticated enough to experience and transmit something analogous to wonder, through technologies that haven't been invented yet, then the argument for biological presence becomes less about necessity and more about preference. And here's where the trajectory of technology becomes genuinely relevant, because the question of whether to send humans or machines to the stars is not being asked in a static technological landscape. It's being asked at a moment when artificial intelligence is advancing at a pace that would have seemed implausible even a decade ago. When robotics is producing systems capable of navigating complex, unstructured environments autonomously, when the concept of mind uploading, the theoretical possibility of running a human consciousness on a non-biological substrate, is moving, slowly and controversially, from pure science fiction into the outer edges of serious scientific discussion, the neuroscientist and philosopher Kenneth Hayworth, among others, has argued seriously that the long-term future of human space exploration may involve not biological bodies or traditional robots, but something in between, uploaded human minds running on radiation-hardened computational substrates, combining the subjective experience and creativity of human consciousness with the physical resilience of an artificial system. The philosophical questions this raises are enormous and genuinely unresolved. Whether a digital copy of a human consciousness is the same person as the biological original is one of the most contested questions in philosophy of mind. But the fact that serious researchers are proposing it in the context of interstellar travel tells you something important about where the reasoning leads when you take all the biological constraints seriously. There's a more near-term version of this argument that doesn't require resolving the hard problem of consciousness. It involves what researchers call distributed intelligence, the idea that an interstellar probe could carry not a human crew, but an extraordinarily sophisticated AI system capable of making complex scientific decisions autonomously, adapting to unexpected findings and transmitting not just raw data, but interpreted, contextualized discoveries back to Earth, not a human scientist, not a simple automated probe. Something in between, a scientific intelligence that can do real science, ask real questions, follow unexpected leads, and send back something closer to understanding than mere measurement. We are not there yet. Current AI systems, despite their remarkable recent advances, are not autonomous scientific intelligences of the kind an interstellar mission would require. But the direction of travel is clear. The gap between today's AI and that capability is real, but it is narrowing. And the timescales involved in any realistic interstellar mission, decades of development before launch, decades of travel time, mean that the AI systems available to an interstellar mission designed and launched in the second half of this century would be radically more capable than anything that exists today. So here's the synthesis. When you take the full picture seriously, the biological challenges, the engineering constraints, the ethical complexities, the generational costs, the trajectory of artificial intelligence, you arrive at a conclusion that isn't about abandoning the dream of reaching other stars. It's about interrogating what that dream actually requires. Maybe the first emissaries to Proxima Centauri won't be human beings in the biological sense. Maybe they'll be something we built, something carrying our science, our questions, our curiosity, our carefully encoded desire to know what's out there. Something that is, in the deepest sense, an extension of us, even if it doesn't breathe. And maybe that's not a lesser version of the dream. Maybe that's actually what the dream looks like when you take it seriously enough to follow it wherever the physics and the biology and the engineering honestly lead. But even if we accept all of that, even if we conclude that robotic and AI-driven missions are the right near-term path toward the stars, there's still a question hanging in the air that this entire video has been building toward. A question that sits beneath the propulsion challenges and the radiation biology and the generation ship ethics and the debate about humans versus machines. The question is, what are we actually expecting to find? Because everything we've discussed assumes that the destination, Proxima Centauri, Proxima B, whatever is out there, is worth the journey, worth the resources, worth the centuries of development, worth the ethical weight of whatever we send, biological or artificial, And that assumption rests on a foundation that deserves to be examined directly. What do we actually know about what's waiting for us at the other end of that 4.24 light-year gulf? What has the science told us about Proxima B, about the system around our nearest stellar neighbor, about the probability that the enormous cost of reaching it would be rewarded with something meaningful? The answer is both more promising and more discouraging than most people realize. And it's going to shape this video in ways I think you'll find genuinely surprising. Let's find out what's actually there. Let's start with what we know, how we know it, and why the knowing is harder than it sounds. Proxima B, the planet that sparked so much of the modern conversation about interstellar travel, was announced to the world in August of 2016 in a paper published in the journal Nature, led by astronomer Guillaume Anglada-Escudé and a team of collaborators from institutions across Europe. The discovery made headlines everywhere: nearest star to our Sun, planet in the habitable zone, Earth-sized. The coverage was electric, and understandably so. If you were going to pick a target for humanity's first interstellar mission, a potentially Earth-like planet around the closest star is about as compelling as it gets. But here's the thing about how Proxima B was detected and why it matters for understanding what we actually know about it. The planet was not seen, not imaged, not photographed in any direct sense. It was inferred from a technique called radial velocity measurement, sometimes called the Doppler method, in which astronomers detect the tiny gravitational tug a planet exerts on its host star as it orbits. That tug causes the star to wobble very slightly toward and away from Earth, and that wobble shows up as a periodic shift in the wavelength of the star's light, toward the blue end of the spectrum when the star moves toward us, toward the red end when it moves away. From that wobble, astronomers can calculate how long the planet takes to complete one orbit and, combined with the star's known mass, derive a minimum mass for the planet. Proxima B completes one orbit in approximately 11.2 days and has a minimum mass of around 1.17 times the mass of Earth. Those are the hard numbers. Everything else, the planet's actual size, its density, its composition, whether it has an atmosphere, whether it has water, whether its surface could support anything we'd recognize as hospitable, all of that is inference, modeling, and educated speculation based on what we know about planetary science in general. The minimum mass qualifier matters. Radial velocity measurements give you the component of a planet's orbital motion that is directed toward or away from Earth. If the planet's orbital plane is tilted relative to our line of sight, if we're not seeing the orbit edge on, we're only seeing part of the wobble, and the true mass of the planet is higher than the measured minimum. Proxima B could be significantly more massive than 1.17 Earth masses, depending on its orbital inclination, which we haven't been able to directly measure. At higher masses, the planet transitions from something potentially Earth-like into something potentially much denser and more geologically alien. There's also the question of whether Proxima B actually exists as described. Science is always a process of verification and refinement, and in 2022, a team of researchers re-examined the radial velocity data used to detect Proxima B and raised questions about whether the signal might be partially or wholly attributable to stellar activity, the same surface churning and flaring that we've discussed in previous parts, rather than to a genuine planet. The debate in the literature is ongoing. Most researchers still consider Proxima B a credible planetary candidate, but the confidence level is not what it was in 2016, and the caveats are real now. Even accepting Proxima B as genuine, and even accepting the most optimistic interpretation of its properties, roughly Earth-sized, in the habitable zone, we immediately run into a cluster of problems that the 2016 announcement headlines mostly glossed over. Problems that, when you examine them carefully, make the Earth-like planet around the nearest star narrative considerably more complicated. The first and most fundamental is what we covered earlier in this series, but deserves to be revisited in this specific context: the nature of Proxima Centauri itself. Proxima Centauri is a red dwarf. More specifically, it's classified as an M5.5 type star, toward the cooler, smaller, dimmer end of even the red dwarf category. Its mass is approximately 12% of the Sun's mass. Its luminosity, the total energy it outputs, is roughly 1/500th of what the Sun produces. That's why Proxima B can be in the habitable zone while orbiting at a distance of only about 7 million kilometers from its star, compared to Earth's 150 million kilometer distance from the Sun. At that proximity, the planet receives roughly the same amount of energy per square meter that Earth receives from the Sun. But proximity to a red dwarf is a deeply different situation from proximity to a Sun-like star in ways that go far beyond the raw energy calculation. At 7 million kilometers, Proxima B sits well inside what's called the tidal locking radius of its host star. Tidal locking is the process by which a massive body's gravitational gradient, the difference in gravitational pull between the near and far sides of an orbiting object, gradually slows that object's rotation until one face is permanently pointed toward the source of gravity. Our own moon is tidally locked to Earth, which is why we always see the same face of the moon from Earth's surface. Proxima B is almost certainly tidally locked to Proxima Centauri. One hemisphere bakes in permanent, unrelenting starlight, the other faces permanent darkness and cold. The terminator, the boundary between the two hemispheres, is a perpetual twilight zone, a ring of dim, slanted light circling the planet. This is not automatically a death sentence for habitability. Climate models have shown that, with a thick enough atmosphere to circulate heat from the day side to the night side, a tidally locked planet could potentially maintain liquid water somewhere on its surface, possibly in that twilight band, possibly even on the day side if atmospheric circulation is efficient enough. But those are models. They assume the atmosphere exists and has the right properties. We have no observational evidence for an atmosphere on Proxima B. None. Every statement about atmospheric circulation and heat distribution is entirely theoretical because we cannot currently observe the planet's atmosphere at all. And here's where the flaring story becomes critical in a new way. We discussed Proxima Centauri's flaring activity in Part 2 in the context of what it means for life on the planet's surface. But it's worth revisiting in the context of atmospheric retention because the two stories are deeply connected. A planet's ability to maintain an atmosphere over geological timescales depends on a balance between processes that add gas to the atmosphere, volcanic outgassing, comet impacts, and processes that strip gas away. The dominant stripping mechanism for a planet as close to an active red dwarf as Proxima B is the stellar wind, the continuous stream of charged particles flowing outward from the star, which interacts with the top of a planet's atmosphere and gradually erodes it. The stellar wind from Proxima Centauri is intense. Studies published in the Astrophysical Journal have modeled the interaction between Proxima Centauri's stellar wind and Proxima B's hypothetical atmosphere, and the results are not encouraging. Without a strong planetary magnetic field to deflect the stellar wind, the way Earth's magnetic field deflects the solar wind, creating our protective magnetosphere, Proxima B's atmosphere could be stripped away on timescales of millions to hundreds of millions of years. Geological timescales are billions of years. Life on Earth took billions of years to develop. The arithmetic is uncomfortable. Whether Proxima B has a magnetic field is unknown. Whether it has a geologically active interior capable of sustaining a magnetic field is unknown. The planet's composition, whether it is a rocky, iron-cored world like Earth or something with a different internal structure, is unknown because we can't directly measure it. We know its minimum mass, we know its orbital period, we know almost nothing else from direct observation. In 2020, a team of astronomers using the Atacama Large Millimeter Array, ALMA, announced tentative evidence for a belt of dust around Proxima Centauri at distances comparable to our own asteroid and Kuiper belts, suggesting the system has had a complex history of planetary formation. In 2019, analysis of existing data suggested the possible existence of a second planet, Proxima C, at a much larger orbital distance, roughly 1.5 astronomical units from the star. In 2022, a third candidate planet, Proxima D, was announced, a small body orbiting even closer to the star than Proxima B, with a mass perhaps as low as a quarter of Earth's mass, making it one of the lightest exoplanets ever detected. The Proxima Centauri system, it turns out, may be considerably richer and more complex than the single-planet picture of 2016. But none of these discoveries change the fundamental observational situation. We are working almost entirely from indirect evidence. The Proxima Centauri system is 4.24 light-years away, close enough on cosmic scales to be our nearest neighbor, and still so far away that even our most powerful existing telescopes cannot directly image Proxima B at all. The planet is lost in the overwhelming glare of its host star, like trying to see a firefly hovering next to a searchlight from several kilometers away. The next generation of extremely large telescopes, the Extremely Large Telescope being constructed in Chile by the European Southern Observatory, expected to see first light in the late 2020s, and the 30-meter telescope planned for Hawaii, may change this picture meaningfully. These instruments, with their unprecedented light-gathering capacity and advanced adaptive optics, may be able to directly image Proxima B and take spectra of its atmosphere, if it has one, for the first time. Spectroscopy of an exoplanet atmosphere can reveal its chemical composition, whether it contains water vapor, carbon dioxide, oxygen, methane, or other molecules. Some combinations of molecules, particularly oxygen and methane coexisting in significant quantities, would be extremely difficult to explain without biological processes and would constitute what scientists call a biosignature. We are not there yet, but the tools are being built, the techniques are being refined, and the solar gravitational lens concept we discussed in Part 4 represents an even more radical possibility for observing Proxima B at resolutions that no conventional telescope could approach. Here's what makes this moment in the history of science so extraordinary. For essentially all of human history, the question of whether other planets exist around other stars was purely philosophical, unanswerable by observation, a matter for metaphysics rather than science. The first confirmed detection of a planet orbiting a Sun-like star came in 1995, less than 30 years ago, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b using the radial velocity technique, work that eventually earned them the Nobel Prize in Physics in 2019. In the 3 decades since, we have confirmed the existence of over 5,500 exoplanets. We have developed multiple independent detection techniques: radial velocity, transit photometry, direct imaging, gravitational microlensing, astrometry. We have characterized atmospheres on some of them. We have found planets in habitable zones. We have found systems with multiple planets. We have found planets around almost every type of star we've looked at carefully enough. The universe, it turns out, is absolutely full of planets, but knowing that planets are common is different from knowing that any specific planet is habitable. And knowing that a planet is in the habitable zone is different from knowing that it is actually inhabited, or even that it has the conditions that life as we understand it would require. The habitable zone is defined astronomically. the range of orbital distances at which liquid water could theoretically exist on a planet's surface given sufficient atmospheric pressure. It's a useful concept. It is not a guarantee of anything. The honest scientific summary of what we know about Proxima B in 2026 is this. We have strong evidence for a planet with a minimum mass slightly above Earth's, orbiting its star at a distance that places it within the theoretical habitable zone around a star that is significantly more active and more hostile to atmospheric retention than the Sun, with no direct observational evidence for an atmosphere, no direct observational evidence for water, no direct observational evidence for any geological or biological activity, and ongoing debate about the precise properties and even the confirmed existence of the planet, as originally described. That is not nothing. The fact that there is any planet at all in the habitable zone of our nearest stellar neighbor is genuinely remarkable, and the probability calculations that went into expecting such a planet to be there are a fascinating story in themselves. But it is also very far from the Earth-like world next door framing that dominated the 2016 headlines. And this brings us to the question that has been lurking beneath the surface of this entire video. The question of what we're actually hoping to find when we look, or eventually go, to Proxima Centauri. Because the most profound version of that question isn't about geology or atmospheric chemistry or even liquid water. It's about life. Is anything alive out there? That question, the oldest and most persistent question humanity has ever asked about the cosmos, is the one we're going to sit with in the final part of this video, not just as it applies to Proxima B, but as it applies to the entire interstellar enterprise. Because the answer to that question, whatever it turns out to be, changes everything. Every calculation about cost and risk, and ethics and timeline looks different depending on whether what's waiting on the other side of 4.24 light-years is a barren, radiation-scoured rock or something else entirely. Let's end where the universe forces us to begin, with a question, not a small question. Not the kind of question that has a tidy answer waiting at the end of a calculation, or a definitive resolution sitting in a journal paper somewhere, or a conclusion that scientists are converging on and will announce at a press conference sometime in the next few years. The biggest question, the one that has been riding underneath every single thing we've talked about in this video, quiet and patient, waiting for us to finally turn and face it directly. Is there life at Proxima Centauri? Is there anything alive, anything at all, in any form, by any definition, on or around that dim red star 4.24 light-years away? Anything that metabolizes, replicates, responds to its environment, persists against entropy through the organized chemistry of biology. Anything that eats, breathes, grows, dies, evolves. Anything that looks up, if it has eyes, if looking up is even a concept that applies to it, and wonders whether it is alone. We don't know. That's the honest answer, and the only honest answer. We don't know, but the shape of our not knowing is itself profound and worth examining carefully, because it tells us something important about where we are as a species and what the interstellar enterprise actually means beyond the engineering and the physics and the ethics. Let's start with what biology and chemistry suggest about the possibility of life in the Proxima system. Life on Earth, as best we can determine from the fossil record and molecular biology, emerged somewhere between 3.5 and 4 billion years ago, within the first billion years of Earth's existence. That's a surprisingly short window, cosmically speaking. Earth formed, cooled, developed liquid water on its surface, and then, relatively quickly, by geological standards, something happened. Chemistry became biology. The precise mechanism is still one of the great open questions in science, but the general conditions are understood. Liquid water as a solvent, a source of energy, the right chemical building blocks, and enough time and molecular complexity for self-replicating structures to emerge. Proxima Centauri is approximately 4.85 billion years old, slightly older than our Sun. If Proxima B exists and has maintained liquid water on its surface for a significant fraction of that time, the raw duration is certainly sufficient for life to have emerged and evolved, at least in principle. Time is not the limiting factor. What is potentially limiting, and this is where the astrobiological case for Proxima B becomes genuinely complicated, is the radiation environment. We've discussed Proxima Centauri's flaring behavior in detail. The ultraviolet and X-ray flux from those flares at Proxima B's orbital distance would be intense enough to sterilize an unprotected surface on a timescale that matters. Early life on Earth was similarly threatened by ultraviolet radiation before the development of an ozone layer, and the ozone layer itself is the product of photosynthetic life producing atmospheric oxygen over billions of years, which is a chicken and egg problem of some complexity. Life needs protection from UV to survive, but the protection came from life on Proxima B without a confirmed atmosphere. The surface radiation environment during flares would be extreme. This doesn't mean life is impossible. Life on Earth has proven extraordinarily creative in finding niches that protect against radiation. Subsurface life, sheltered beneath meters of rock or ice, would be entirely shielded from surface radiation events. Ocean life beneath even a few meters of water would be similarly protected. Life doesn't have to live on the surface, it just has to live somewhere, and planets are large, layered, complex objects with many potential somewheres. There's a broader concept in astrobiology called the radiation life paradox for red dwarf systems, and it cuts in an interesting direction. The same stellar activity that makes the surface of a tidally locked red dwarf planet so hostile to complex surface life also provides a continuous energy source that could, in principle, power chemosynthetic ecosystems, communities of microorganisms that derive energy not from sunlight but from chemical reactions, the way life exists around deep-sea hydrothermal vents on Earth, completely independent of the Sun. If Proxima B has a geologically active interior generating hydrothermal systems, the possibility of subsurface or deep ocean microbial life cannot be ruled out at all. And here is where astrobiology intersects with one of the deepest and strangest puzzles in science: the Fermi paradox. If you're unfamiliar, the Fermi paradox is named for physicist Enrico Fermi, who in 1950 reportedly asked, during a casual lunch conversation with colleagues, a deceptively simple question: where is everybody? The universe is approximately 13.8 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, the majority of which appear to host planetary systems. The conditions for life, at least life as we understand it, seem to be widespread. Intelligent life capable of technology has been present on Earth for at least tens of thousands of years. Given enough time and enough stars, civilizations capable of interstellar travel or communication should have emerged long before humanity, and yet we observe no evidence of them, no signals, no megastructures, no visitors, no artifacts. The cosmos, as far as we can determine, is silent. The paradox matters in the context of Proxima B because it frames the question of life there not as an isolated inquiry, but as a data point in a much larger question about the prevalence of life and intelligence in the universe. And the range of proposed resolutions to the Fermi paradox is itself a kind of map of the possible answers to the question of what's waiting at Proxima Centauri. Some resolutions are optimistic in their implications. Maybe interstellar travel is simply harder than we imagine, and the first 9 parts of this video have certainly made that case. So civilizations don't spread across the galaxy, even if they exist. Maybe intelligent species tend to turn inward toward virtual realities and inner exploration rather than outward toward the stars. Maybe signals are out there and we haven't been listening in the right way, at the right frequencies, with the right technology. These resolutions leave open a universe potentially teeming with life that simply hasn't reached us yet. Some resolutions are darker. The one that cosmologist and author Stephen Webb calls the Great Filter Hypothesis suggests that somewhere on the path from simple chemistry to spacefaring civilization, there is a step that is extraordinarily, almost impossibly difficult, a bottleneck that essentially no lineage of life successfully navigates. If the Great Filter lies behind us, if it is, say, the emergence of the first self-replicating molecule, or the development of the eukaryotic cell, or the emergence of multicellular life, then we are extraordinarily lucky survivors of a process that almost always fails, and the universe around us is full of worlds where life stalled out at some early stage. If the Great Filter lies ahead of us, if it is something that technologically advanced civilizations routinely encounter and fail to survive, then the silence of the cosmos carries an implication that is, once you sit with it, genuinely chilling. The question of what we find at Proxima B is, in this framing, one of the most consequential scientific questions imaginable. If we look, whether through telescopes, through gravitational lensing, through a probe sent across 4 light-years, and we find nothing, a barren rock, radiation-scoured and airless, no atmosphere, no water, no chemistry that suggests life ever took hold. That result, while disappointing on one level, might actually be reassuring in the Great Filter framing. It would be consistent with life being rare, which would suggest the Great Filter is behind us rather than ahead. If, on the other hand, we look at Proxima B and we find biosignatures, atmospheric oxygen and methane, or complex organic molecules, or any chemical signal that points unambiguously to biological processes, the implications cascade outward in every direction at once. Life existing independently at the nearest star would mean that life is not a cosmic accident. It would mean that the chemistry of life is something the universe does readily, given the right conditions, on geological timescales. It would mean that the galaxy almost certainly teems with biology, and it would make the Great Filter, if it exists, something that lies ahead, something we haven't encountered yet. The astronomer Carl Sagan spent much of his career arguing that the discovery of even microbial life elsewhere in the universe would be one of the most significant events in human intellectual history. Not because microbes are impressive in themselves, but because of what their existence would imply about the universe we inhabit. A universe where life is common is a fundamentally different place, philosophically, spiritually, scientifically, from a universe where life is a freak accident that happened once, on a pale blue dot in an unremarkable corner of an ordinary galaxy. And Proxima B is the nearest possible place we could look for that answer, 4.24 light-years away, close enough that light-speed signals take only 4 years to cross the gap, close enough that the most ambitious near-term propulsion concepts might actually reach it within a century, close enough that the solar gravitational lens, pointed in exactly the right direction from 550 astronomical units out, might reveal its surface features in enough detail to search for the signatures of biology without any spacecraft ever leaving our solar system. This is the context in which the entire journey we've traced in this video has to be understood. Every challenge we've catalogued, the distance, the propulsion, the radiation, the biology, the psychology, the ethics, the unknowns about the destination, every single one of them exists in the shadow of that question. The hardness of the journey is real, but the reason the journey is worth contemplating at all, worth funding, worth the intellectual energy of the best scientists and engineers of our generation, is that the destination is not just another point in space. It's the nearest possible answer to the oldest question we've ever asked. So let's pull everything together now. Let's stand back and look at the full picture we've assembled over the course of these 10 parts. The journey to Proxima Centauri is hard in ways that are not fully captured by the phrase 4 light-years away. It is hard because the distance is genuinely incomprehensible in human terms, and the speeds required to cross it in any reasonable time frame are far beyond anything we've achieved. It is hard because the interstellar medium, the seemingly empty space between the stars, is a radiation environment and a particle hazard that becomes more severe the faster you travel through it. It is hard because every serious propulsion concept involves engineering challenges of a scale and complexity without precedent in human history. It is hard because human bodies were not designed to spend decades in microgravity and cosmic radiation. It is hard because the psychology of prolonged isolation in a sealed environment pushes against the grain of everything human beings evolved to need. It is hard because generation ships, if that's the path we choose, raise ethical questions about the rights of people who never consented to the mission they were born into. It is hard because the destination may not be what the headlines suggested in 2016, and our ability to know what it actually is remains limited by the capabilities of instruments we haven't finished building yet. None of this means we shouldn't try. None of this is an argument for giving up or looking away. The history of human exploration is the history of attempting things that seemed impossible, encountering hardships that exceeded expectations, and continuing anyway, not because the destination was guaranteed to reward the effort, but because the drive to know, to reach, to extend the boundaries of the possible is so deeply woven into what we are that abandoning it would mean abandoning something essential about being human. But it does mean we should be honest. Honest about what the journey requires. Honest about what we don't know about the destination. Honest about the gap between the inspiring rhetoric of interstellar travel and the hard, specific, unsolved problems that stand between here and there. Not because honesty kills wonder. It doesn't. Real wonder is not fragile. It doesn't need to be protected from difficult facts. It actually deepens when it has to make room for the full complexity of what the universe is presenting. The universe is presenting us with something extraordinary here. A star 4 light-years away, around which there may be a world, maybe barren, maybe alive, certainly remarkable. And the fact that we, a species that spent most of its history not knowing other stars had planets at all, can now point a telescope at that star and detect the gravitational wobble of a planet 1.17 times the mass of Earth, orbiting every 11.2 days at a distance of 7 million kilometers around a star we couldn't even see with the naked eye 2 centuries ago because it's too dim. That fact alone should stop you for a moment. We found it. From here. With light and mathematics and the patient, cumulative, collaborative effort of thousands of scientists across decades, we found a planet next door. Now we want to know what's on it, and that desire, that irrepressible, quintessentially human desire to know what's over the next ridge, what's beneath the next surface, what's waiting at the end of the next impossible journey, is not a problem to be solved. It's the thing that has carried us from the savannah to the moon, and from the moon to the edge of the solar system, and from the edge of the solar system to the first trembling, uncertain, astonishing steps toward the stars. The journey to Proxima Centauri is harder than you thought, much harder, every part of it, and that's exactly why it matters. And if this blew your mind, you're going to want to click the video on the screen right now, because we explored how long Voyager 1 would actually take to reach Proxima Centauri. And the answer is so absurd, it puts everything you just watched into a whole new perspective. You don't want to miss this one. See you there.